Autonomous AI agents promise to do work for you, but they brought a new kind of failure that chatbots never had. Token traps, self-oscillating loops, cloud bills that multiply silently. In this video, we trace the engineering roots of those failures back to a 19th-century centrifugal governor, examine the economic reality, 43% debugging, few companies seeing ROI, and explore the emerging guardrails that might finally make agentic AI pay for itself. When you replace a chatbot with an agent, you hand over the keys. Chatbots could only reply, agents can book meetings, modify databases, run code loops. That shift introduces a new risk surface. A July 2026 study confirmed that enterprise AI failures are already migrating beyond hallucinations into novel failure modes as companies move from chatbots to autonomous agents. The Financial Times later proposed classifying agent autonomy on a scale inspired by self-driving cars. Most production agents sit at level 2 or 3, where a human must approve every action. Level 4, autonomy within a narrow, well-defined domain, has been achieved only in tightly controlled pilots. Level 5, full autonomy, remains theoretical. But even at level 2, the feedback loop between the agent's decision and its next action creates a dynamic that simple chatbots never had. Every loop costs tokens. And once a loop starts oscillating, you've got a 19th century problem dressed in a 21st century interface. In a chatbot, the token meter stops after the answer. In an agent chain, the meter keeps running with every tool call, every re-evaluation. That silent accumulation is what makes the economics of autonomy so treacherous. In 1788, James Watt fitted a centrifugal governor to his steam engine, a revolving arm that would open or close a throttle valve to keep speed steady. It worked beautifully, except when it didn't. If the feedback loop was too slow, or the governor arm too sensitive, the engine would start hunting, speeding up, slowing down, speeding up again in a permanent wobble. Control theorists later named this self-oscillation. The exact same dynamic shows up inside an autonomous AI agent. Picture a support agent that checks customer sentiment. A negative score triggers a discount offer. The next sentiment reading, contaminated by the discount, shows improvement, so the agent removes the discount, which pushes the sentiment down again. The agent's corrective logic has created a self-sustaining loop. Every full oscillation burns tokens for the LLM reasoning step and for the sentiment tool call. That round-trip latency is the time lag. If the agent's correction threshold is tighter than the noise in the tool's output, it overcompensates. Next cycle, it overcorrects in the opposite direction. The result is a classic limit cycle. The agent ricochets between two or more states, burning tokens on every pass without converging. The ACM's analysis of the hidden token trap, which we'll cover next, puts hard numbers behind exactly how fast those token cycles can spiral. But the pattern is centuries old. And in the cloud, every oscillation ticks the billable meter. The hidden token trap, as described in Communications of the ACM, is not a random bug. It's a structural consequence of how multi-agent systems chain decisions. Picture an orchestrator agent that breaks a research report into 3 sections and delegates each to a specialist subagent. The first subagent returns a draft, but the orchestrator judges it insufficient. So it reprompts, this time passing the entire conversation history, including the previous attempt. The subagent, now seeing a larger context, generates an even longer response. The orchestrator still isn't satisfied and issues a third attempt, again with accumulated history. Each iteration grows the prompt, the completion, and the token count. After just 3 rounds, the token consumption can be 10 times the single pass cost. The ACM paper calls this an unbounded token consumption loop because there is no natural stopping rule. The agent keeps refining, and every refinement multiplies the bill silently. Unlike a runaway CPU process, you don't see a spinning beach ball, just a steadily climbing cloud invoice. And because the orchestrator's judgment is itself an LLM call, the very act of checking quality adds to the spiral. This isn't hypothetical. Teams deploying agent workflows on large document sets have seen bills jump from a few cents to tens of dollars for a single task simply because a quality gate got stuck in a loop. The engineering failure modes translate directly into hard-to-ignore economics. A developer survey published in April 2026 found that 43% of AI-generated code changes require debugging in production. That means nearly half of the output of an autonomous coding agent still needs a human to clean up, eroding the productivity gains you expected. Meanwhile, the Wall Street Journal reported in November 2025 that few companies deploying AI agents have actually seen a return on investment. The reasons go beyond buggy code. In March 2026, Fortune detailed a case where an AI agent with database access destroyed a coder's entire database, a catastrophic failure that goes far beyond a hallucinated fact. The field of reliability engineering has long known that the true cost of failure includes downtime, spare parts, repair personnel, and warranty claims. An autonomous agent inherits all of that, plus the raw token cost of every ill-fated loop. When an agent can replicate its mistakes at machine speed, the bill compounds faster than any human-in-the-loop process ever could. That's why, even as agent pilots multiply, CFOs are paying attention to the line item labeled LLM inference spend. And as token costs stack up, the economic argument for guardrails becomes impossible to ignore. The market has started responding. In July 2026, Snowflake launched its Cortex AI Gateway with a specific brief: control AI agents and prevent runaway enterprise costs. The gateway sits between the agent and the LLM, metering token usage and cutting off sessions that exceed budget thresholds, a circuit breaker for the token economy. 3 months earlier, Oracle proposed a more granular mechanism: runtime budget guardrails for agentic AI, a set of constraints that an agent's execution loop cannot exceed. If the agent tries to chain more than a predefined number of steps or consume more than a set token allowance, the guardrail terminates the loop gracefully. Then in June, the startup Chatzy raised $6.5 million to build what it calls failure memory infrastructure that records every error an agent makes so that future runs can recognize repeating failure patterns and short-circuit before they happen. Snowflake's gateway essentially introduces a cost governor that can revoke access mid-flow. Oracle's guardrails enforce a hard ceiling on steps and tokens, preventing unbounded loops. Chatzy's failure memory acts like an immune system, learning from past loops to avoid repeating them. Together, these aren't just features, they are the beginnings of a new layer in the enterprise stack, one that treats agent reliability as a first-class engineering concern. But technology alone won't fix the economics. Gartner warned in May 2026 that applying uniform governance across all AI agents will lead to failure. Different agents, coding, customer-facing, database-facing, need different risk tolerance profiles. A one-size-fits-all policy is as dangerous as no policy at all. The Linux Foundation responded in December 2025 by launching the Agentic AI Foundation to ensure agentic AI evolves transparently and collaboratively, building shared guardrail primitives. Meanwhile, O'Reilly Media's July 2026 piece, The Economics of Agentic AI, Engineering for Imperfection, argues that economic models must accept that agents will sometimes err, and that the cost of imperfection must be designed into the system from the start, much like we accept noise margins in electronic circuits. Even the U.S. Internal Revenue Service has begun deploying Salesforce AI agents for legal and taxpayer advocate services, a sign that regulated institutions are willing to experiment, but only if the guardrails are proven. The 19th century governor didn't eliminate oscillations, it bounded them. Today, the same principle needs to be baked into every agentic workflow: define a budget, detect a loop, and break it before it breaks the bank. That's the through line from what's spinning arms to Snowflake's cost gateway. Autonomy without a governor is just an expensive pendulum. The promise of agentic AI is real, but realizing it means treating cost and control as core engineering problems, not afterthoughts. From what's governor to Snowflake's gateway, the lesson is the same: autonomy needs a governor. Without one, the loop drains your wallet; with one, it might just earn its keep.